Alright, so we're going to start talking about a significance test for a mean. Alright, so our mu, in which case our conditions are a little bit different. And that's what we're going to talk about here with moving forward. Because our conditions, yes, somewhat the same with verifying that they're random, you're normal, and that you're 10%. But to determine if they're normal, we got to do a little different test, which you've probably seen before, but we're going to talk about it. So again, we're going to talk about the conditions here. So your conditions. Okay? So in your conditions, again, you need to have a random sample, right? Random sample. In which case they may say something like, in the problem it's a simple random sample, or they may just say random sample. But you want to have a random sample. And I'll just go put sample under here, just so it makes a little bit better sense. Okay, so that's going to be one thing that get checked off. Alright, so our next thing, we want to find out if it's normal, right? So we want to determine if it's normal. Well, there's three things that could play out to determine if it's normal. So one of the three things need to be checked off. So the first one we're going to talk about here, we simply could just say population is normal. So this population is, let me get the is a little bit away from that abbreviation there. Population is normal. Now this will be stated in the problem. So in other words, it won't give you as far as so much of a sample size, it won't show you any other type of data. They're just simply going to say population is normal. Alright, so that's what they're going to talk about with that. You can use that by stating your conditions. Another one here that you'll probably be familiar with is, of course, our central limit theorem. In other words, the sample size, right, or n, is greater than or equal to 30. So again, that is going to be central limit theorem. Now, when you write this out, yes, simply put CLT and then write n greater than or equal to 30, and then write the actual value you have for your sample size. So fill in the number you got for n, show this greater than or equal to 30, put a little check mark. Be like, this is all good. It works out. Okay? I know it sounds tedious, but those have to be written out because, again, you have to act like I do not know what you're talking about. You've got to explain why you did what you did. Now, if they didn't give you sample size, if they did not say population is normal, let's say they gave you a dot plot or histogram, something showing the data that they're talking about, giving you the values, then you see the shape, okay? Well, in this case, hopefully, you'll see that it shows no strong skew. You don't want to show a strong skew. It needs to look fairly symmetric, normal shape. Okay, so no strong skew or outliers. You don't want to have any outliers on there, okay? So it needs to be a normal bell-shaped curve that you could get from the data points, as well as no outliers are shown as far as the data they give you in a dot plot or a type of graph representation they give you, okay? And then, of course, our last thing we're going to talk about that you guys have probably dealt with and understand, our 10% rule, okay? So our 10% rule. So again, that is simply saying that we have our sample size is less than 10%, or 1/10, of the capital N, which is our overall population, right? So I'm just going to put that in parentheses, that's your population, right, of the whole thing. Okay? So, in other words, if you take a sample of students from high school, that's the sample you get is less than 1/10 of all high school students in the United States, let's say. Okay? So, that's what you're looking at for 10% rule. Again, simple random sample. You need to just have a random sample to be able to move forward with the test. The population is normal, central limit theorem, or if the data shows no strong skew or outliers, that just shows you that the curve is going to be approximately normal. Okay? Again, put that in your head. Approximately normal. Okay? So approximately normal, and then your 10% rule allows you to move forward with the calculations for the do part of your state plan to conclude. Allows you to use your formulas to calculate your p-value for comparison. Okay? So let's look at an example here and see how that plays out.
Hey, this is Jason Molesky. In this example, let's review how to check conditions. This figure shows a dot plot, a box plot, and a normal probability plot of the battery lifetimes for a simple random sample of 15 batteries. Let's check the conditions for carrying out a significance test of the company's claim about its deluxe AAA batteries. Well, let's first start by checking whether or not our random condition is met. The company tested a simple random sample of 15 new AAA batteries, so this condition is met. To check the normal large sample condition, we first start by noting we don't know if the population distribution of battery lifetimes for the company's new AAA batteries is normal. In this case, we have a fairly small sample size, n is only 15, so we'll need to inspect the data for any departures from normality. Now the dot plot and the box plot together show some slight right skewness, but no outliers. Further, the normal probability plot here is fairly close to linear. So combining these three features, we should note that we should be safe performing a test about the population mean lifetime mu. Finally, the 10% condition. Because our batteries are being sampled without replacement, we need to check that there are at least 10 times 15, or about 150 new AAA batteries. I'd say this seems reasonable to believe, so the 10% condition is met.
Alright, so now that we've got the conditions, now let's talk about doing your tests and coming up with your values here, okay? So again, remember when we're dealing with means, you need to find something a little bit different here, right? You can look at degrees freedom. So degrees freedom, which is df, and that is equal to your sample size minus 1. Always be your sample size minus 1. Okay? So with that, the reason why I'm telling you that too is a little bit different. You know, we normally write out our normal curve, we draw it out, and we give our little curve here, and we normally say n for normal, and we give our mean and our standard deviation. Well, when you're dealing with the actual means value, so doing this test for the mean, or we're dealing with degrees freedom, to show that we're calculating this using our degrees freedom, they can simply be labeled as a t, and then label with your degrees freedom value. In other words, they'll explain that these tails may be a little bit fatter, a little bit skinnier on the ends there for your calculations. Because it's not exactly going to be set up as a normal curve dealing with proportions. Okay? So, in dealing with your t score instead of your z score, okay? So we're going to be dealing with, in this case, a t score instead of a z score. So, with your t score, that is going to equal t is going to equal your x bar, right? The mean from the values you got from the data minus the actual mean, the actual mu, all divided by your standard deviation, in which case it's going to be standard deviation for your x bar of your sample divided by the square root of your sample size. Okay, so you got to use that calculation to calculate your standard deviation when dealing with your means. The other thing will be a little bit different here. It's going to be calculating for your p-value. Since we're dealing with your t-score and dealing with degrees freedom, we're going to use something a little bit different than our normal CDF. So when you're calculating for your p-value, you're calculating your p-value, it's going to be a TCDF. This will be the notation for that. Now, to get to that, if you have a TI Inspire, easiest way to do that is menu 655, and that'll get you to a TCDF. Now, when you're writing out this TCDF, even if you're to look up in the table, using the table to calculate these values, which is an example, we'll talk about using that as well, because using your degrees freedom, you can actually look on a table to view your value for your p-value. When you write that out, though, you simply follow the TCDF, okay, and it's going to be labeled by, you will list out your lower bound, your upper bound, and the only thing it's asked for is your degrees freedom. So when you do this, this will give you your p-value. That'll give you the area under the curve based off the data you put in for your lower bound, your upper bound, and your degrees freedom. Okay, so again, the key things here are your notation for your normal curve. You can simply write out a T instead of an N, and then write out your degrees freedom. Just write out the value you got for your degrees freedom, which degrees freedom again is your sample minus 1. Okay, and then to find your t-score, the value based off the data given to you, you take that mean that is given to you minus the overall mean divided by standard deviation for the sample, right? So which is standard deviation divided by the square root of the sample size, and that'll give you your t-score value. And based off of that, then you can go into finding your p-value and using your TCDF, menu 655, and then write it out. If you use a calculator, write this out, right? Write out, you wrote TCDF, parentheses, lower bound, comma, upper bound, comma, degrees freedom, and yes, write the numbers there, but then label what those numbers are. Label which number is your lower bound, which number is your upper bound, which number is your degrees freedom. So therefore, someone, a reader who's grading your test, like myself, will understand what you're talking about for those values based on the normal curve, or approximate normal curve that you have depicted from the data. Okay? Now, if you're going to use a table instead of a calculator to calculate your p-value, then you can use a table similar to the one, they call it in the examples table B, which I believe is the updated table. The table that I gave you listed in Canvas is table D for your t-distribution critical values. So these are upper tail probabilities. So with this, based off your degrees freedom here, okay, so again, you have your degrees freedom right here going down this way, whatever you're looking at, and then you're going to go off of whatever degrees freedom, then you're going to find the t-score value wherever it either falls or falls in between. So let's say you had a degrees freedom of 8, say a degrees freedom of 8, and you calculated a let's say t-score of 0.9. Okay, well 0.9 would fall in between 0.889 and 1.108. So it'd fall right here in this range, right in between those two values. So therefore, you would have a p-value that falls between 0.15 and 0.2. So that would be your p-value based off that. Again, you wouldn't have an exact p-value, but that would give you a p-value, that range that would fall in between those two values, between 0.15 and 0.2. So you can base that off of, you can use that information to base your final conclusion on whether or not you're going to side with your null or alternative hypothesis. Okay. So again, it doesn't give you the exact value, but you gives you a range to base off of and move forward with. And it explains better in the example that we're going to go off of. Again, they say table B, but the table that we have listed is table D, the one that I gave you on Canvas. So don't let that confuse you. Again, just using the tables based off your T distribution is what you're going to be looking for. Okay. So let's watch this example and see how that plays out.
Hey, this is Jason Molesky. In this example, let's perform a significance test for mu. The level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along a stream, and the results in milligrams per liter are noted here. Now, a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. So for this problem, we need to figure out whether or not we have convincing evidence at the alpha equals 0.05 level that the aquatic life in this stream is at risk. And then given that conclusion, determine which kind of mistake, a type 1 or a type 2 error, could we have made, and explain what this mistake would have meant in context. Well, to start with, let's state our problem. We want to test a claim about the true mean dissolved oxygen level mu in this stream at the alpha equals 0.05 level. Our hypotheses are the null hypothesis that mu equals 5 against the alternative hypothesis that mu is less than 5. If the conditions are met, we should do a one-sample t-test for mu. So let's check those conditions. First of all, the researcher measured the DO level at 15 randomly chosen locations, so our random condition is met. For our 10% condition, we notice there's an infinite number of possible locations along the stream, so it isn't really necessary to check that condition. Finally, for normal and large sample, we don't know whether the population distribution of DO levels at all points along the stream is normal. With such a small sample size of only 15, we need to look at the data to see if it's safe to use T procedures. We note that the histogram looks roughly symmetric, the box plot doesn't show any outliers, and further, the normal probability plot is fairly linear. So with no outliers or strong skewness, the T procedures should be pretty accurate. Now, let's actually do the problem here. We entered the data into our calculator and did one var stats. The sample mean here is 4.77, and our sample standard deviation is 0.9396. For our test statistic, we note that our sample mean minus our hypothesized null mean, 5, over our sample standard deviation divided by the square root of the sample size is negative 0.94. For the p-value, we note that the p-value is the area to the left of t equals negative 0.94 under the t distribution, with 14 degrees of freedom, one less than our sample size. Now, table B shows only areas in the upper tail of the distribution, but because the t distributions are symmetric, the probability that t is less than negative 0.94 will be exactly the same as the probability that t is greater than positive 0.94. Now note, because the observed t lies between 0.868 and 1.076, our p-value falls between 0.2 and 0.15. Now we can also use technology to find the exact p-value. The tcdf command on your TI calculator would give you an exact p-value of 0.1816. Notice right where we thought, between 0.2 and 0.15. So because this p-value is greater than our significance level, we failed to reject the null hypothesis. We don't have convincing evidence that the mean DO level in the stream is less than 5 milligrams per liter. Now, because we decided not to reject the null in part A, we may have made a type 2 error. That's where we fail to reject the null when it really is false. If we did, then the mean dissolved oxygen level in the stream would actually be less than 5 milligrams, but we didn't detect that with our significance test.
Alright guys, so hopefully that helped explain how to do the significance tests for the means a little bit better, and definitely using the table to calculate your probability for your p-value and moving forward with that. Alright, so again, I know it looks like a lot of writing and everything else, which again it is. For this 4-step process, it takes a little bit of time, because it's not just worrying about the numbers that you calculate, because that's not the key point. The key point is describing how you came up with those numbers and what those numbers mean, what you're taking away from that, and what it's concluding overall according to the findings. So remember, list out all that information, everything for your state, everything for your plan. The do part, your calculations, you guys are pretty strong with that and understanding how to do the number calculation. That's great. But you need to go forward then to actually do your conclusion and writing out what is happening, what side you're going with, if you're rejecting the null, if you fail to reject the null, and how that plays out overall according to your data values you get from your p-value related to your significance level. Okay, so again, make sure you got everything listed there for your conditions, and then going forward with understanding how to get your degrees freedom and your t-score value, and then calculating your p-value. Again, TCDF, menu 655, and your TI inspired makes it super simple if you're able to use that while you're doing your check your understandings. You guys will be able to use that during testing, so hopefully you get used to that and can practice that a little bit. Other than that, if you are unable to use that, again, don't be scared with that, because you can always use the tables. The tables will give you the same conclusions overall based on your t-score values. Okay, so with that, hope you learned a little bit something that cleared a few things up for you, and I'll see you next time.